So we're going to continue on with our types of reactions, and this time we're going to focus on the single replacement reaction. So we want to know exactly what the single replacement reaction is about, and how can we figure out what's made when a single replacement takes place. So a single replacement reaction will have an element and a compound reacting with one another. And in this reaction, that element is going to replace one part of the compound. And in doing so, it's going to form a brand new element and a brand new compound. So if we have, element A reacting with a generic compound BC, element A is going to replace one of the elements in compound BC, which means it's going to be removing one of them to become its own independent element and no longer in the compound. So if element A replaces element B in the compound, you're going to form a brand new compound, AC, and you're going to form element B on its own. So you were replacing one part of a compound. So the two scenarios we want to look at here are when metals replace each other and when a metal is used to replace a hydrogen atom. So when we discuss metals replacing each other, the one thing that we need to be aware of is known as the activity series. The activity series is a ranking essentially of the activity of a metal. Any metal that's higher up on the activity series can replace a metal that is below it. And that is just kind of the hierarchy here. So let's look at our example of magnesium reacting with silver chloride. So we need to consult, first off, the activity series to know if this reaction is even possible. Just putting two things together doesn't actually guarantee it's going to react. So if we just examine the two metals, magnesium and silver, on the activity series, magnesium is all the way up here, silver is pretty far below. So considering that magnesium is higher up, it is able to replace the silver because silver is less active, meaning it has less of a hold on that chlorine atom. So we know this reaction is going to work, and that's kind of what we want to look at with the activity series first. Will the reaction even happen to begin with? So now that it's going to happen, we need to kind of figure out exactly what's going to be made from it. So you can kind of approach this in different ways, but you can't neglect the fact that ions are going to be involved because you're going to be making some kind of ionic compound. So it's always helpful to kind of list out the ions for all the elements initially so that you have this to work with. So magnesium's got a +2 charge, silver has a +1, and chlorine takes a -1. And we want to do this because A, we can actually see how or why certain things are going to rearrange the way they are, and because it's going to save us the trouble when we actually have to figure out what's going to be made, which of course I'm showing you here, but I'm going to work out anyway how we got there. So knowing that this is a reaction, your products are going to be different than your reactants. Okay, so they should all be different. So knowing initially that the silver was bonded to the chlorine means that in the product, you're no longer going to have silver bonded to chlorine. Now, we know that the two metals are going to replace one another. And the reason why we know this is because if we just look at their charges as ions when they're in this solution, well, magnesium is a cation, so is silver, and chlorine is an anion. So if the silver chloride can no longer be a thing because it has to change since a reaction's happening, two elements need to bond together. Well, magnesium and silver can't bond together. They're both cations. Positive and positive don't go with each other. Silver and chlorine can no longer be together because they have to be different. So that kind of leaves the combination of magnesium and chlorine left. And again, we already know, because that the metals are going to replace one another, that the magnesium is going to end up with the chlorine. But this is how we can tell, because the positive has to go with the negative. The +1 can't be with the -1 anymore. We have to change it up. And so that's where magnesium is going to come in. So now that we know our ions, the magnesium and the chlorine are going to bond to one another, it's just a matter of getting the chemical equation correct. And this is where, we're just going to go ahead and crisscross to get our compound formula, MgCl2. Now that magnesium and chlorine are bonded together, the silver got replaced. So now the silver is going to be alone. And you can see how the different metals have essentially changed places. You have magnesium no longer alone, it's in that compound with the silver. The silver, sorry, with the chlorine, and now the silver, which wasn't a compound, is going to be alone. They switched their roles. If we examine another scenario like this, let's have aluminum react with copper 2 chloride. So first off, we want to check, does this reaction even work? Well, aluminum right up here, copper all the way down here. Yes, aluminum can replace the copper. So we know this reaction can work. So then it's a matter of, let's list out these ions. Okay, we know that the metals are going to replace one another. Aluminum and copper are going to switch spots. Aluminum has its +3 charge. Copper here is going to have a +2, and our chlorine will have its -1. So when it comes to forming the products, one of our products is going to have aluminum and chlorine now, because it's going to switch spots with the copper. So we're going to have aluminum with its +3, chlorine with its -1. Crisscrossing them gives me the product AlCl3. And now, since the copper got replaced, it was removed from the compound. So the copper is going to be alone. And then it's just a matter of balancing this equation, in which our full balanced equation comes to 2, 3, 2, 3. Now, it's really common to ignore the fact that ions are involved and actually keep the subscript of 2 for the chlorine when we make this new product. So I'll see a lot of students actually make AlCl2 because they assume, well, there was a 2 on the chlorine originally, so it should be there at the end. And that's not the case. And it's not the case because the chlorine has the 2 initially in this first compound because it's bonded to an element that has a +2 charge. But now it's with a new element. It's with aluminum that has a +3 charge. The amount of chlorines is just affected by the charge of the cation that it's with. So if you're going to change the cation, it may affect the number of chlorines, and that's okay. We will just balance it afterwards because it's going to change. And that's where students typically have the most difficulty with, just kind of understanding that subscripts are independent from the different compounds. What you have in one compound may be different in another compound for the same element. That's fine. That's the whole point of balancing the equation, because they're going to change sometimes. So while it may be tempting to keep the subscript the same, never do. Sometimes it'll work out that way, but not always. And so it's always safer to assume use the ions and don't use the subscripts as your guiding point to making the product formula. So here we just saw 2 metals replacing one another in a compound. So now let's take a look at a different example where we are replacing hydrogen atoms. So we're going to look at 2 scenarios with replacing hydrogen: when you replace a hydrogen in a molecule of water, and when you replace a hydrogen in a molecule of acid. So when you react a metal with water, you are going to form some iteration of the metal hydroxide and hydrogen gas. So your products are typically always going to be the same when reacting a metal with water. It's just a matter of, adjusting the metal hydroxide to the very specific metal that you have. And if we actually go back to the activity series, you can see that hydrogen is ranked here. And it's going to follow the same rules, that only the elements above hydrogen can actually replace it. So all these elements above hydrogen will actually react with water. The ones below it won't. So if we want to kind of figure out why it makes a metal hydroxide and why it makes hydrogen gas, you can actually work this out to look kind of similar to what we did with the metals replacing each other. But that requires rewriting water in a different, less common form, especially if you're just learning chemistry. So let's kind of take this reaction of sodium reacting with water, and we're going to rewrite this to be a little bit more familiar. So we're going to have sodium, and when it reacts with water, we're going to rewrite water in its acid-base form. So instead of having H2O, we're actually going to rewrite water as HOH, which is still H2O, except in this form, we are acknowledging an acidic hydrogen and a basic hydroxide group. Water is neutral. It's amphoteric, meaning that it can be both an acid and a base. So if we write it in this way, you can actually see this exchange similar to what we saw in the metal replacing metal. So in this case, we know that these two things are going to react, and this metal, sodium, is going to replace a hydrogen. So if the sodium just replaces hydrogen, similar to what we saw if it was replacing a different metal, this sodium with its ions, okay, +1 for the sodium, hydrogen, let's give this a +1, and hydroxide, we know, takes a -1 charge. Replacing it like this puts the sodium with hydroxide. So we end up with NaOH. Then we're going to have hydrogen alone. Now, metals, all of them are monatomic. Hydrogen, though, is diatomic. So if the hydrogen is going to be alone, then it just needs to be H2. And you can see that matches exactly with the products that we predicted. So this is how you can kind of explain or kind of tell that it forms a metal hydroxide and hydrogen gas, and it's just kind of seeing it the exact same way as if this metal was replacing another metal. And this exact same thing is seen if you're doing this with acid, where you have this acidic hydrogen, and the metal is just going to go ahead and bond to that anion. So if we were having magnesium react with hydrochloric acid, the hydrogen and the magnesium will simply switch their places with one another. The magnesium is going to end up bonding to the chlorine, making magnesium chloride, and the hydrogen is going to end up alone, which is going to produce H2, hydrogen gas. And again, the thing to note here, yes, the chlorine does not have a subscript initially because it is bonded to hydrogen, but when the chlorine bonds to the magnesium, okay, we have to adjust the number of chlorines because it is now in an ionic bond, and the magnesium with a +2 charge is going to affect the number of chlorines. And again, that is okay for the subscript to change. We will balance this equation afterwards because it changes. So in the single replacement reaction, you are really just replacing one part of the compound. And the whole key to figuring out the products is ions. Listing out the ions, really important, and it kind of makes looking at this a little bit easier.